Let me display, share screen.
भोइस त ठिकै छ होला है मेरो सुनिएको
एकदम ठीक छ
ओके
All right. Thank you, Dr. Orial, for inviting and introducing me. I hope everyone can hear me well. Is that correct? Sunya sir.
एकदमै राम्रो आछ
Perfect.
भोइस पनि पर्फेक्ट
Very good. All right. So I'm gonna talk about an overview of nanofabrication, as Dr. Orial already mentioned. I'm currently at Physics and Material Science and Engineering Commercialization Research at Texas State University, United States. So just to reiterate the same thing, Dr. Orial already introduced me. Just one thing I wanted to mention. So I had been a faculty in Kathmandu University from 1995 through 2004. And that's the reason I left Kathmandu University in 2004, not in 2002. So that is the only thing I wanted to add here. So it was in December 2004, I was there until, and then I moved to United States end of December 2004. So I started my PhD program in 2005 January. And then I completed in 2009 and moved to work for Intel as a process engineer. Worked there for 9 years approximately before I changed my mind to get a different feel of working for a different corporate facility. And that was in Texas. Samsung Austin Semiconductor, it is called. Very similar job role. It's different facility, different culture. And that's the reason I wanted to have a different feel. And that's the reason I moved. But working for Samsung for 3 years, from 2017 through 2019 August. Finally, I decided to go back to academia again because I had a prior experience of 10 years in teaching in Kathmandu University. And 4 years while I was doing my PhD in State University of New York, based on my experience in Nepal. I was given adjunct faculty position, so I had been teaching there also, so 10 plus 4, 14 years. And then approximately altogether 11 years working for corporate. Finally, I decided to go back to academia because of some known reasons that I'll talk about briefly on the subsequent slides. So that's me. And I don't have to spend too much time on the slide because Dr. Orial already mentioned everything about me. There is one thing, when I was doing my PhD, I had several collaborative projects with General Electric Global Research that I have here in the item Research and Semiconductor Process Technology Development Engineering item. That is something I wanted to mention because that gives a glimpse of the difference between being in academia and working for a corporate facility. Despite my several projects and several papers ready to be published in the research project with Global Research, I was not even included in my thesis because of the IP issue. And that is the first time when I realized if you work for a corporate or if you do any collaborative research with any corporate, you have to be careful that you are not going to be able to publish your work. All right, let's move on. So on this page, it's just a glimpse. So two things I'm gonna spend time on the slides on. One is what I will not talk about due to the intellectual property restrictions. Because I had been working for Intel for approximately 9 years, and it's top secret facility, research and development of the entire Intel corporation that is there in Portland, Oregon, in the United States. That is where all the technologies are developed. So a few things I'm not going to talk about, and those are listed here. The first bullet point, equipment configuration. It's kind of a feel of being on a different planet if you go to the fab in Intel, and Samsung also. They have, their fab is very big fab, large in size, and also very clean. So 1 in 1,000. If you have 1,000 particles in unit volume in a regular operating room, their clean room has one particle in that particular volume, if you compare that way. So it's that clean. And then the equipments, all I can say is one equipment may be costing around $250 million US dollars, that expensive. And there are several equipments like that. If you enter there in the fab, you'll feel like being on a different planet. You will not think that, okay, this can't be on this earth, something like that. That is what I felt when I first entered into the fab after I was hired by Intel, and then I got in there. So equipment configuration is something I will not talk about. I will not talk about process flow. There are several steps, 100 plus, 200 plus steps or operations that will start from the bare silicon to make the functional device. It takes around 3 months if you do on expedited basis. So there are several steps, and how the flow works, I'm not going to talk about that, obviously. The chemical details, I will not be talking about any chemical details, any patterning mechanisms. Chemical details means what chemical you use, what chemical is compatible for the photon interaction with the materials to do the patterning and how it works. I'm not going to talk about that. Those are also top secret things. And design, the layer details, how you make the design and how you build the layers on top of other layers to make a working device. What the reticles are, what the layout of a reticle is. I'm not going to talk about those things. I will not present any pictures or images from IP. No any IC layout. IC means integrated circuit layout. I'll not be talking about any numbers from IP. What thickness, what lines and holes, CDs, critical dimensions. CDs means critical dimensions. I'll not be talking about those things. This is something I have to mention whenever I present the nanofabrication things. I have to mention this for the IP issues. At least to keep in the record that I had mentioned in the beginning. What I will talk about in this presentation is basically nanofabrication mechanism in general, not in detail, but general. Basics of process engineering, SPC system, statistical process control system, research and technology development in brief, why the technology development is needed, and why people do the research and technology development in semiconductor fabrication facilities. Why is this needed? We'll talk about that. The fab culture and activities in any fabrication facilities, no matter where you are, could be in Intel, could be in Samsung, could be in IBM, could be in TSMC, could be in global foundries, wherever you go, as long as there is fabrication facilities, very similar culture and activities you will find. Equipment health monitoring and troubleshooting. Little bit I will be talking about what the role of the troubleshooting and equipment health monitoring is in the fabrication. And then in the end, I'll add a little bit of the physics and material science and engineering commercialization research at Texas State University, where I am currently at. So this is something I have to mention before I start my talk. What I will talk about and what I will not talk about. Let's move on. Now, research potential in USA. Two aspects of it. And this presentation, maybe in the future, I'll do another seminar, time permitted. And then I'll continue from what I will wind up today. So I can go a little bit into more details, keeping the IP restriction in mind. But then today's presentation, this presentation is expected to give some information for any potential PhD candidates who may be planning to come to United States, and any faculties who may be planning in the similar areas, materials characterization or nanofabrication for the postdoc or whatever. So this is what is expected from this talk. So two aspects of the research potential in USA. Based on my experience, this is what I have thought, and this is what I would let other people know about. So the first is research at corporate facilities. For example, Intel, Samsung, Global Foundries, IBM. There are others also, Micron, you name it. So the research basically, wherever you go, obviously there are three types of research people are involved in: theoretical, computational, and experimental, of course. In the corporate facilities, as I mentioned, very expensive equipment, but very precise. You are looking into talking about the nanometers. If you have 0.005 nanometers, you can't miss 1 0. And if you make 0.005 at 0.05, that may bring excursion of making the company lose millions of dollars, and then you will not see yourself there. So that precise equipment, and that's the reason it's very expensive. As I said, $250 million for one equipment, and you will be seeing thousands of equipments like that once you get in the fab. That's the reason I mentioned you'll feel like being on a different planet. They have enough budget. You don't have to worry about any money. They have enough budget, enriched resources, of course. Direct realization of the applications. Whatever you do there, your research, your activities, everything brings the direct realization into the real life applications. You just don't do something today and wait for the result into coming to the realization in real life applications next year. It's not like that. It has to happen right away. No external publications, of course, because whatever you do, any innovation, that's not yours. And that is something I wanted to mention here. Research at corporate facilities. Anything you do, that's not yours because you are getting paid for doing that. So whatever you do, it's their property. And that is what I mean by saying intellectual property. So you cannot talk about anything you do there. There has been instances, someone in the past, 10 years ago, someone in the past quit the job, went somewhere else, and didn't realize that he was not supposed to talk about the IP things. He did that and he was sued, and then he had to suffer a lot of complications. So you can't do that. Of course, this is high paid research at corporate facilities. If you work for any corporate facilities, you get paid really high. But then that is at the cost of being always under watch. So you will feel like you are always under watch. You are being watched by 50 people. Your day and night, you don't count how much you are working. if you have to execute your plan and present the data tomorrow, and if you don't do that because when you go to the meeting tomorrow, you say, okay, I had some family matters to take care of, and that's the reason I was not able to get it done. That is not an excuse. So you are always under watch, but then you get paid really high. So the work-life balance, I have put a question mark here. I don't want to say poor because there are so many people, myself, I have worked for 11 years for the corporate, but then I can't say, okay, it is poor work-life balance, but there is a compromise. And good for young blood. Again, I put question mark there because I don't want to say, okay, this is only good for young blood. This is good for anyone who can deal with it. But then you have to eat, sleep, breathe the work. You are eating, thinking of the work. You are sleeping, thinking of the work. You are breathing, thinking of the work. And that is the life when you work for a corporate facility, when you are involved in research at corporate facilities. Research at academic institutions. So I said two aspects of it, and the second aspect is the research at academic institutions. Again, theoretical, computational, experimental, everything is there. But then you have limited equipment, limited budget, limited resources, but everything is open to you. You have freedom of publications. Whatever you do, you just stay connected with the world. You can have it published. So you have full freedom of publications. But it is low paid. It's okay, leave me alone. I get paid low, but I'm fine. I don't have to be under watch. I'm living my life, so I have better work-life balance. I feel like I have better work-life balance. That's all you can think of. It's, again, question. I can't claim that it is only good for elderly folks. No comment, it's good for all, I would say. But normally, the young blood, you can meet the expectations of the corporate policy guidelines when you are young. But when you get a little older and older, sometimes health issues, sometimes family matters, all those kind of things. So there is always a compromise. I don't want to comment anything on these two aspects, but there is always a compromise and you have to deal with it. You have to live it. So this is what people normally find in the United States, whether you are involved in the research at corporate facilities or you are involved in research at academic institutions. So two aspects of it. Okay. Now, let me start with the research activities at corporate facilities first, and then I'll move to the academic institutions. So the soup to nuts at corporate facilities. The soup to nuts means what you start with and what you end up with. So when you are having a meal, you start with the soup, you finish your main course meal, and then you start chewing the nuts. So from start to the end, what people do in the corporate facilities. Intel, Samsung, wherever. So the main thing is the research and development. It starts with innovations. And then whatever you do in your innovation, you do the process validation. The process word is important here because your innovation for the fabrication, nanofabrication facilities, it can't be just one thing. You do it today and then it's done. It doesn't go that way. Whatever innovation you make, you have to define several steps, as I said, 100 plus steps, and how you can make the working functional device. So there are so many steps. The overall mechanism is called process. This process involves so many, the recipes, chemicals, equipments, all those kind of validation you have to do. So innovation, first you make your innovation, do the process validation, and once you are convinced that your process, your innovation is stable, you can do it, then you do the implementation, implement it, And once you have implemented it at the research facilities, then Intel, Samsung, all these corporate facilities, they have the research facility at one place, and then they have the high volume manufacturing facilities at other places. So the research facilities, you do the innovations, process validation, implementation, and then you spec it. Spec means write the specifications. The specification is something that you write. It has to be several, maybe 100 pages of one process, one type of process. But then that is something you give to other high volume manufacturing facilities, other people, they will have to follow whatever you have done at the research. So just to mention here, when I was Intel, I had written several specs, maybe over 2 dozens of specs, but that is something I cannot talk about. So once you have done that, then you are good. And then you move to a next technology node, and then you have sent everything to the high volume manufacturing facilities. But before you do that, you have to have some 4 or 5 seeds, we call them seeds, from other facilities that you train them, and then finally give the specification written well. And then they will follow, they will go back to their facilities, and then they start doing the high volume manufacturing. High volume manufacturing is, that is the goal of the company, because you do the research, but then they have to have the high volume manufacturing done so they can make money. They can sell to the customers, they can contribute to the world, they can make money. That is their goal. So high volume. But then at the high volume manufacturing facilities, they don't do research, but then what they do the sustaining. They have to sustain the process that you have developed at the research. They have to do the troubleshootings, of course. The troubleshooting means if the equipment is not working properly, if something fails at some layers, then they have to do the troubleshooting. They have to make sure the module is robust, no any hiccup, it runs flawlessly, and most importantly, the defect, that is the killer. You can't have any defect. A small speck of a particle or anything can kill a die that you make on the wafer. But then if that is there, if one die is killed by the defect, then the end device will fail the e-test. So then it's not working, it's not functional. So that's the reason I put the defect is the killer. So you have to do all those things to make sure your quality is controlled. And then baseline or yield improvement, when you do that, you got it. That is what the company tells you. All right, yield improvement. Yield means they invest on the process, on you, and their end goal is they want to get 90%, 93%, 92%. Okay, they may be greedy, they may want 100% yield, because whatever this, it's just kind of the efficiency, what you get to what you pay for. So what they pay in overall and what they get, so that is the yield. So every time, every single day, whatever you do, your activities go towards improving the baseline in the statistical process control system charts, and eventually they have to improve the yield. So that is basically overall they do in the corporate facilities. But this is just to give some bullet points, but then we'll go over the detail. So as I said, end result, an overview of nanofabrication and research at corporate facilities. The end result is a functional device. And that functional device, you'd be surprised, it is known to all. It starts from sand and brings it to the real life applications. And this is a functional device schematic that you can use it. So from sand, it starts from the sand, and then you have it everywhere. You drive your car, you have the electronics. You fly a plane, you have all the electrons in the plane. You have your air conditioning, you have the heating system in your house. Wherever you go, you have your smartphone, you have a computer, laptop, everywhere you go, you'll find the application of these functional devices. So everything starts from the sand, and then it brings to real life applications. So this is the end result. And then, as I said, it starts from the wafer, and wafer is the great thing here. So that's the reason I put here wafer the great. Now, what is wafer actually? The wafer is something that comes from the sand. You make the silicon ingot. Let me, okay. So silicon is purified, melted, and cooled to form an ingot. And then the ingot on the left picture on this slide, you can see those are the ingots. Depending upon what type of wafer you want in your fab, normally the circular type, but some research academic institution, they also use some rectangular or square type. So that's the reason we have both kinds of ingot here. But circular is the one that everywhere the corporate facilities like Samsung, Intel, TSMC, they use the circular type because their equipment is made to handle this circular type wafer. So then once you make the ingot, after purifying, melting, and cooling to form an ingot, then you make the slices. And each slice you can see in the middle picture, that is the wafer. Each single slice is called the wafer. The chronology, I'll talk about the technology nodes, different technology nodes starting from micron scale to the nano scale. We have the upcoming slides and we'll talk about that. But then depending upon the technology nodes, right now, everyone is using, at least Intel, Samsung, they are using 300 millimeter diameter wafer, 300 millimeters, 30 centimeters diameter. But back then used to be 8-inch, this is 12-inch, 200 millimeter, 100 millimeter, all those kind of things. So then they started making bigger and bigger. So the size, the larger the size, the more die you can make on one wafer. But then their production, they do the calculation every day. They want to get 3,000, 6,000 in 3 months. They want to get 100,000 wafers out by making the chips. And that is how they do the calculation so they can make money. Because they pay at least $50 million in one day, just the salaries for all the employees. So they have to get the wafers out. So that's the reason the larger the size, the more die you can make it. But then that doesn't mean that you can make, okay, a 500 millimeter wafer and get it started right away. That's not possible because then your equipment configuration has to change accordingly. As I said, all the expensive equipments, all the process that you develop, all the automation system, how the robot works in the fab, everything has to align accordingly. So it's not possible just to make it larger and then let it go. So then I was just talking about the wafers in the middle, and then you can see on the rightmost picture, you see the beautiful, colorful pattern there. That is how you make the chip. That is just an example. The wafer, you start with the bare silicon wafer in the middle, and then once you start processing, then you see the patterns, how you make it. All those patterns you see, I'll have another slide for you to take a look. And then it's a very complicated circuit that you make on the wafer through very complex process. So if you think of billions of transistors diffused in a very small dimension that you cannot see each transistor with eyes, because that's the reason this is nanofabrication of the nanoscale level. So then you can think of now, it's not possible to make it with hands. So everything has to be automated, and it is the chemical engineering with the photonic interaction. Everything goes that way. And that is how it has been possible to make it. So you have all the circuitry, everything is complete, they're integrated circuit. very small dimension, and you have billions of transistors diffused, and everything is connected to make a complete circuit, so you can have the functional device. And that is the reason it takes 3 months, approximately 3 months, to get complete device out. So the last bullet point was hiding there. So chips are built in a grid formation on the wafer. I have already talked about the rightmost picture on it. Okay. Now this slide is the continuation of what I already talked about on the previous slide. The question is, what's in a fully processed wafer? And you can see on the left, top left picture, there are 3. One on the left, on the top left, is just the wafer. And then in the middle, you process it. And then the encircled one is showing the pattern there. And then you have so many, there's like that on the wafer. And then you have the very complex circuit. I'll leave it there for a minute for all of you to take a look, especially the diagonal on the bottom left and the top right, these 2. So you can see all those are the circuits that people make in the corporate facilities. And then you have the functional device bottom right. You can see how they have been. If you try to make that physically using the wires, analog type of thing, it will not be possible even to accommodate everything in a big conference room if you just use the wires. But you do that on a very small dimension, very small size. So everything is done by the light and chemical engineering mechanism. So just take a look, all the complicated circuits, and then you get the functional device. And that's the reason it takes approximately 3 months to make it. All right. So now let's move on. So then you have already seen the complicated circuit, and everything starts from the bare silicon. I will have another slide to summarize everything in general, though there are several other steps in between, but I'll just summarize in general. But then before I do that, on this slide, you can see it starts from the bare silicon, and think of building a house. You do the construction, and then you do one on top of other, 3 stories building, 10 stories building, maybe 50-story building, something like that. So that is how you. But then when you think of building a house, 50-story house, it's not like that. It's a larger scale. But here, the nanoscale engineering. So overall, you will see maybe 1 millimeter, 1 centimeter length, and then within 1 centimeter, you will have several layers, and that is how we make it. But it starts from making the transistors, the source, the drain, and the gate. And then that is the first thing you make. And then to complete the circuit, you keep making layers on top of layers, layers on top of layers, and then do the lines, the contact, vias, holes, lines and holes, lines and holes, all these things, and then make a functional device. So this was just to show you how we made it. This is one picture that tells you, you can see here, the source and drain, starting from the bare silicon, how you make it. So you do the source and drain, you do the polysilicon, you can see, and then once you start making the metals and contacts, you can see the metal line, and then the contact means the via, the hole that you use to connect one to the other. And then you make the gate. So source, drain, and gate, that is the concept of transistor, just like you roughly equivalent to, I'd say roughly equivalent to saying emitter, base, and collector, just like that. So the gate is something that defines the different technology nodes, and then based on the gate width, we'll have different technology nodes, and that is the chronology I'll put in one of the slides, upcoming slides, the need of different technology nodes and why people do that based on the gate width, and why we have to keep shortening the width. All right, now the question is, how is it possible? And as I said, it's through very complex process. And in general, the fundamental operations, as I said, there are several operations in between, but then the fundamental operations are the silicon wafer production, of course. And once you have the wafer, then you do the cleaning, you do the oxidation, and then you do the lithography. This lithography, photolithography basically. Photolithography means you use the concept of the photon interaction with the chemicals that you use. So lithography, and then the ion implantation and the etching. So lithography and etching, they go one after another for each layer you build there. So you have to do the lithography. Photolithography means you have to do the patterning based on the design layer you have already made on the reticle photo mask, and then you print that. So lithography, the word lithography is coming from the concept of printing something in place. So the same thing you do in this technology also, but this technology is not just like the printing in a place. This is kind of everything is done by the laser, and then you use the mask. The mask is actually what has all the design, the circuitry design, the layer, everything else. And then you shoot the reticle with the light, the laser, and that is also something you have to characterize which technology node you are talking about and what feature size you are printing on the wafer. The feature size means the feature that you involved to make the functional device. The feature means the line or the STI or any other layer, or the vias, the holes to make the interconnects, all those kind of things. Every design, everything. But then it's not just one layer that you use the mask and shoot it with the light and then print on the wafer, and then you are done. It's not like that. So you have done one, and then on top of that one you have to do the other, and then if you do other layer on top of the first one, then you have to make sure everything is aligned. There is a slight deviation will cripple it. So then you will ruin the process, and no mistake is allowed there. So the lithography and etch, they go one after another. The lithography uses certain type of chemicals that is that you have to make compatible with the photon, the laser, the wavelength of the laser that you use, or the immersion photolithography technique. But then whatever design, whatever feature size you have marked on the photo mask, you print 1/4 of that size on the wafer, 1/4. Okay, and then some technology nodes, they were dry process, and then it was difficult to print a smaller size. And then later on, the immersion lithography came in that use ultra pure water, the refractive index 1.4 approximately, and then that reduces the size to much smaller that you intend to print on the wafer. And then deposition. So everything, this is just the fundamental operations, and then you keep repeating for all the other layers. But then there are several steps. It's just everything you do on the wafer, it has to be followed up with the validation to make sure your critical dimension of the feature size that you have printed, you have patterned on the wafer, is meeting your expectation. It doesn't have any defect, because you started today and there is a speck of a particle coming from the equipment sitting somewhere, and then you keep processing that, and 2 weeks later you have put a lot of efforts, a lot of resources, a lot of materials you have used, and then later on you realize, you find that it failed the test subsequently, and then everything is wasted. You are not supposed to do that. So that's the reason there are several steps in between that provide you the validation to make sure everything is all right. So then, through all these complex processes, the technology development is what is needed. And why is it needed? Because the company wants the high performance device and the cost effective production also. It has to be cost effective. It's not like, and that's the other main difference between the corporate facilities and the academia, because you cannot make the company to invest several $1 million on your project, and in the end you give something that is much less than that, so the company is going in loss. You cannot make that. So it has to be cost effective. So innovation, to start from the innovation, you have to convince, okay, this is the innovative work, this is what is going to work, but we have to validate it, of course. And then you have to do all the graphics design, do the development. Automation is the main thing because it has to go through the high volume. And then the human, you can't rely on the human. Everywhere you can make mistake. Human is to err, right? So to err is human. So you can make mistake and no mistake is allowed. So everything has to be automated. Not only from that perspective, some mistake perspectives. Also the time consumption, the efficiency. If you make it automated, everything goes flawlessly by itself. But human, if you have to carry one photo mask from one equipment to other equipment, and while carrying you may drop it, and then one photo mask costs $130,000, and then you break it, and then you are done. Okay, so you are not supposed to do that. Everything is automated. The robot will come and then pick it up and then carry from one place to another place, and you have everything set up in automation. And that is also something amazing that you will see in the fabrication facilities. Everything is automated, at least in Intel, Samsung, Global Foundries, TSMC in China, everything is automated. Okay, and then comes integration. There is an integration team that analyzes everything if there is any issue coming from any process step, and you have to make sure everything is working the way they are supposed to. They have been intended. And then electric test, and then you do the implementation and then send it to high volume manufacturing. I have already mentioned before. Now, let's talk about a little bit of, I have talked about the fabrication thing and the process, innovation, technology development, their expectation, and how you make it. But then let's talk about a little bit the fab culture and activities, what they do, just a glimpse. As I said, the cleaner, 1,000 times cleaner than a regular operating room is the fab. And then the culture, the fab culture and the activities. You'll be surprised to know the floor that we call the technician's floor in the fab, shiftly coverage 24/7. Operation never stops unless there is a earthquake and all the equipment shut down. Unless there is a big power bump or power failure, even if there is a power failure, they have automated system, comes back on. But then even the fraction of second of power bump will cause the equipments, all those precise and expensive equipments to air out. And then they will not do anything. So then the operation stops there. And then all the engineers who are the tool owners, equipment engineers, they have to do the troubleshooting. They have to requalify the equipment. Just like if something goes wrong in the plane, unless it is fixed and it is certified by their authorized person, the pilot is not allowed to fly the plane to risk the life of all the passengers. Just like that. So if something happens, a fraction of second of power bump, the equipment engineers, they have to qualify the tools before you can bring it back to production, up and running. You cannot do that until then. So the fab culture, the fab management is the shiftly coverage. I will tell you one thing, shiftly coverage 24/7 operation never stops. Even if it doesn't stop, you are not bothered in the Christmas. They give one night, approximately one night, kind of the happy break. If something goes wrong, it will just stay there. They will not bother you the Christmas. Other than that, it never stops. All right, and everything is automated. I have been talking about no mistake. Troubleshooting, as I said, the tool equipment engineers, they have to do the troubleshooting, investigate where the issue is coming from, no matter whether it is in the product or the monitors. Monitors means you have the regular monitors, station monitor, they're called, that you monitor the health of the tool. Tool means equipment. The word tool refers to the equipment you are using to the manufacturing. So the monitors, the reticle issue, there is a reticle engineer. They deal with the reticle. Reticle is another important thing in fabrication. Reticle is also called the photo mask. The reticle, the photo mask is what has all the pattern, all the circuit design, everything else. And that is something, otherwise, there is no way you can pattern to make the circuit on the wafer with your hands. There is no way. So everything is done by light. So you have the reticle, you shoot the reticle, the photo mask, and then you print on the wafer. So that is the reticle I'm talking about. That reticle has all the designs, all the features. But let me tell you one thing, sometimes the reticle design is also becomes problematic. And then when your test fails, then you have to redesign, you have to correct the issue, any feature that you have on the reticle. If that was not done properly, then it comes out one way or the other, you'll find it. So the mismatch, any defectivity on the reticle, because the reticle, they have several describe and the feature and the chrome, transparency, everything else, transparency, everything else. But then sometimes it grows kind of defect there. So you have to make sure it gets cleaned properly, but it's not like just you wipe it down and then you clean it. It's not like that. There is a procedure. Everything has to follow the BKM, best known method. That is another important thing in the corporate facilities. You keep using BKM, best known method. Everything has the BKM. You have to follow the BKM. Tool health monitoring. As I said, station monitor, module specific, automation, SPC charts. Every day, every single day you follow your SPC chart. Statistical process control system. So everything is based on statistics. Preventive maintenance. All the equipments have to go through the preventive maintenance. You have quarterly, you have weekly, you have annually. There are certain equipment preventive maintenance items that they have to follow. Make sure equipments are run, because equipments are the thing for the fabrication facilities. Okay. New product information, depending upon what the customers want and how efficient the device has to be. So they keep introducing a new product, and the CEO will ask you, all the employees, to make sure everything gets done in, for example, 2.5 months. Then it has to get done in 2.5 months. There is no exception. Okay. So then that is something that puts in pressure. And that's the reason when I said you are always under watch, that gets multiplied 10 times when there is a new product introduction and expected to be out in certain number of weeks or something. So then any new product when introduced, you have to, that is customer oriented, of course, and then you have to do all the layer quals, and then you have to take it to full automation, and that is something that you do in the fab. And then even if you do that, sometimes there is a process issues. So the process issues, and if you are the layer owner, you own the layers, then you have to do all those investigation whether there is issue coming from the chemical, dispense or composition, everything. Critical dimensions is not good. The critical dimension that you print, for example, you print 30 nanometer, and then it is expected to be 30 nanometers, but then you get it 40 nanometers or 20 nanometers. I'm talking in nanometers, not in meters or something, nanometers. So if it is expected to be 30 and your statistical process control system allows you based on the sigma standardized, you have standardized it. So if that is only your process window is only plus minus 2 nanometers, for example, you can't go above 32 nanometers and you can't go below 28 nanometers. So it has to be within that. Otherwise, if it goes to 34 nanometers, and then that will cause overhang or short circuit and the devices will not work. So you cannot do that. So all those process issues is very critical. You have to deal with it. And then sometimes something goes wrong. For example, what if you intended it to be 30 nanometers and you got 40 nanometers? But then that is something when you measured it, then you knew. If you don't measure it, you don't know. So you measured it and then you knew that it is 40 nanometer. What do you do then? It's already processed. Do you want to send this for the further step? No, you cannot do that. Then what do you need to do? You have to rework it. So the rework, again, that means whatever you deposited, the layer you deposited, following all the procedure, deposited the chemical, you did the patterning, you made the critical dimensions of the fissure size, but then it failed, and then you have to redo it. How? You have to scrub that layer. But then when you scrub it, then you cannot impact the layer underneath. And that is what brings it kind of more complicated situation that you have to deal with. So then you have to define the layer specific rework process. So when you want to rework it, you scrub it, but then you have to define what chemical you are going to use and how long and what is the rate and how you are going to do it so it doesn't impact the underneath. Okay? And then you can redo it, and then you can adjust, you can tweak it, your process, so you can get it to 30 nanometer. So that is the rework process you have to define. Defectivity in the killer, I already talked about. You can't have any defect because the equipment that you are using, you are depositing certain layers, you are exposing it, you are doing all those process steps, but then even if it's clean, it is clean, but then equipment has to run through the robots. The equipment is the equipment made of all the metals, all the metals components, and then it has something going on inside the equipment. It may put some particles, something somewhere, rubbing or something, and then you have to make sure it is defectless, no defect. And then sometimes, as I said, design related issue on the reticle itself, you have to correct it. And then overall integrated issue. And that is kind of more challenging if you don't know where the issue is coming from. For example, you deposited 10 layers, and after 10 layers, then you see the problem. It is failing the test. And then you have to investigate everything from bottom to the top, 11 layers. There are several steps in between. And then you have to find where the defect is coming from, where the problem is coming from, where the issue is coming from, and that gets challenging. And then to do that, you have to investigate all the data. The data, as I said, everything is automated. So you can use your laptop, even if you are at home, pull the data, do the remote connection to the system, and they have all the data stored. So you can pull the data, do the data analysis, make your decision where the issue is coming from, and then ask the module owner to take a look. But this gets challenging. So that is called the overall integrated issue. So this is the fab culture. This is the activity that you can see in the fab. I just wanted to mention everything related to the fabrication and fabrication for those even in the United States or from Nepal. If you happen to come to the United States in future, you want to pursue this type of career, then at least you know, or even if you are in Nepal, steps. I cannot go through all of those. As I said, maybe in the next continued seminar talk, I can go a little more details, keeping the IP in mind. But then today, just I wanted to take one example, the photolithography process. The photolithography process, it starts from the photoresist coating. Actually, the photolithography process, the one I was talking about, printing in a press, just like resembling with the concept of printing something in the press, the same thing you do here in the photolithography process. You print the pattern on the wafer. The pattern that you have on the reticle, you print the 1/4 size of that onto the wafer to make the backbone or the skeleton or the circuit design for the function device. So it starts from the photoresist coating. So you have the equipment, you do the spin coating. So it does the spin coating. Okay, so the chemical is dispensed, and then the wafer is rotating, spinning, and that is the reason it is called spin coating. And then you have the thickness, again, in terms of the nanometers. So then that is something I mentioned. I will not talk about that, but then it is of the order of certain nanometers. So you use the thickness, and it is layer specific. So that thickness coating you do, and then once it is coated, there are other steps. You do the baking, so as to make sure it is stable there, and then it goes to the exposure side, and then it gets exposed. The exposure side, the equipment is what you use the reticle there, and then shoot with light, and then make the pattern on the wafer. So then you will spin it, spin coat it, and expose it, send to the scanner, expose it, and then get it back to the spinner module again, and then you develop it. There again, you use a different type of chemical that develops it. Whatever pattern through the light, the photonic reaction, with the photoresist. Photoresist is the chemical that you use that is compatible with the wafer or with the underneath layer that you have already deposited. And that is something that can interact with the photon that you are using, for example, 193 nanometer of laser light, 248 nanometer of laser light. So that photon reaction, that makes that pattern stay there. And then when you send it to the developer, that you use a different chemical, again, that is something you have to characterize based on your layer, based on your technology node. Those are the things you do in the research facilities. So then you have to use that, so it gets developed, the exposed area and unexposed area, depending upon the positive type of photoresist you used, chemical, or negative type of photoresist chemical you used. And then when you develop, then exposed and unexposed, and then you send it to the etch, and the etch area will just remove it, and then you make the pattern. So on the wafer, for example, you want, this is concept, and then you want one small area to not have anything, and the other area to have a line or a hole, something, and that is what you do. So you do the exposure, develop it, send it to the etch, and then they use another type of chemical, and that, because of that, scrubs out one area that is not wanted and leave the other area that is wanted. And that is because of the development that you do in the spin area and the exposure things. All those combinations go together. Okay, so then it starts from there, photo is coating, and then you send to the exposure area. That is where you use the optical mask. That is what I have been talking about, the reticle. And then roughly 1/4 you print on the wafer. The stepper is where you expose. That is called the scanner. And that scanner is very expensive. That is what I have been talking about. $250 million, $260 million, depending upon what technology node you are talking about. And they have very, very, very precise equipment components. Everything is done by the lens. And then for the immersion lithography, there is the water, ultra pure water also. And laser is using 193 nanometer. That is something I can talk about because that is spread out all over the world, so everyone knows. So 193 nanometers, that one. And then it goes to the development, that is something I already talked about, and then goes to the etch, and then rinse, spin, rinse, and dry, and then you have the pattern, and then make sure you are getting the critical dimensions you intended to have. That is something, again, if you don't get what you intended to, then you have to rework, and it keeps going. So this is one process step that I wanted to present here, for example, but there are several other steps. Now, technology development, I already talked about. The goal is from bare silicon wafers to functional devices, cost-effective, robust process for safety, quality, output. They call it safety, quality, and output in corporate facilities. Safety number one, quality number two, and the output is number three. But other than safety, sometimes the big people, the big powers of the company, they want to make a good compromise between quality and output. Sometimes they want to get output, 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 right? And then how? So then technology development, all the bullet points I have put here in the how: define architectural integrated design, process flow, define layers and their process steps. And the process steps, as I said, I'll not talk about all these things in details, but I can at least give as a nomenclature. The fin that you start with, gate, source, drain, dopants, implantation, diffusion for electric properties, metal layers, you do the interconnects, you do the planarization, and then you do the features analysis, the metro cell in all the features. The pitch is another important thing. Critical dimensions, process window, you have to define the process window, how much flexibility you have to get a certain layer into place. And then alignment strategy. The alignment strategy is also important because, as I said, you will start building, like erecting your house 50-story, and then you don't want the house to go like this. It has to align, it has to be erected straight. So there is a slight margin in the alignment strategy also. So if the alignment strategy is failing, then you have to redo it again. So that is also another important thing you can play with. Tool type, like what type of tool, equipment you need, what tool configuration, exposure type means what laser type, exposure type means what kind of laser you are using, 248 nanometers or 193 nanometers, or combined with the immersion or EUV, extreme ultraviolet, or DSA, directed self-line, self-assembly, all those exposure types you use. This then selection of the proper photoresist, that is the chemical, what thickness, what the swing curve suggests you to get the thickness, what spin recipe you want to make, how fast you want to spin, if you want to give some acceleration or the spin speed, and how much chemical is being dispensed, all those kind of things you have to define the recipe, and the scanner recipe also. And then targeting, you have to do the scanning electron microscopy also. That is something that you use to measure the critical dimensions. The scanning electron microscope, there are so many tools you have to use being in the fab. The reticle qualification, the defects optimization, and then you develop etch process, rework process. Bark is the bottom entire reflective coating, and there is a slant coat also, sacrificial light absorbing material, and there is ILD, interlayer dielectric, there is a hard mask, there is a passivation, etc., etc., etc. There are so many in between. Then the metro sampling design, how many data point you want to collect, so that fits into your mean sigma standard deviation limit. And then the raise for the develop check critical dimensions, for the final check critical dimensions, all those kind of things. So based on the contour, all those features characterization you have to do. Then you pick a test lot, whatever process you designed, and then you pick up test lot, and then you do all the characterization with this test lot, because you don't want to start 100 wafers at a time and ruin all the wafers. You don't want to do that, and that is not allowed. So you pick one test lot, and then you do all your processing steps, and then you collect the data from the automation, and then you do the analysis, and then finally you claim that you can praise yourself like, oh, you did it, and you did it. And then you can set it up for the next step. And then to do that, because it's so extensive, it's so complex, one person cannot do everything. But then there is a module, different module engineer you have to coordinate with. And then, but the person who does the integrated type of thing, they have to do the coordination with the defect metrology, integrated management team, yield people, and then you do it. Because you make the plan, you make the project, you make sure the plan you made gets executed. Otherwise, it is you who owns the project, and you have to make sure it gets done. So you have to make the coordination with the team. And then the troubleshooting, of course, the data analysis, tool issues. The troubleshooting means whether the issue is coming from the tool, equipment, or the process. And when it is tool issues, then, and you are the process person, then you are good. You are good in the sense that you don't have to have that headache in your mind, because you can just ask the module or equipment engineer, shut down the tool. Okay, you cannot run your tool. This is the issue coming from your tool, and then you fix it before we can run anything. Your tool is shut down. Once his tool is shut down, and then his manager, his area manager, so why is the tool shut down? Okay, that from the process, and then you have to fix it then. So then his night is gone. If it happens in the night, his night is gone until it is fixed. Okay, but then if it is process issue, and if I am the process owner, if I am designing, or if I am owning all those layers, then I have to make sure the process issue gets fixed, and then that is my headache. So then, but that is of course more challenging, and details is coming from here. So process issue, generally being the plan executor, you have to do the data analysis for all the layer, all the gross failure analysis. GFA means gross failure analysis. You have to involve defect metrology, integration, defect type, what type of defect, what is the EDI impact, expected die impact, how many dies are getting impacted on the wafer. Okay, that is also something you have to make sure you have that beforehand. And then it requires, then based on whatever analysis conclusion you have made, you have to make a model, you have to plan it, and then you have to make sure the changes in process happen to get the issue fixed. How you do it? Then there is a procedure for the process change. You have to pilot it. Pilot means you have to test it, pick a lot, and then based on your model plan, whatever change you are making, process change. Process change means that involves so many things: the chemical, the rate, the exposure type, many things happen and they, get involved in there. So then you have to make changes, and then you have to run a test lot. That is what you call pilot, and then you write the white paper. This is called white. This is something you cannot get published externally, but then that remains in the company. That is their property, and that is what I was talking about. And then you have to do the implementation of the change, and then do the specs and send it also to the high volume, because you found the process issue, and that process is also run in other fab facilities like in Intel. They have in Arizona, they have in New Mexico, they have in Israel, outside of the United States also. So I used to get several seats coming from the Israel, some other fabs. I used to train them. So that is kind of another type of experience here. But anyway, so that is there. So that was the general process issue. But the lithography, talking about that again, whether it is coming from the spin or expose, any recipe issue, any station monitor defects, any no excuse flow for the quick turn monitor, any depth meter roll-off, any targeting issue, there is a coherence matching issue, there is a feature characterization issue, there is a FMEA called failure mode engineering analysis, there is a OPC evaluation, optical proximity correction evaluation, there is a mask modification as needed, pilots roll-up, process window skews, a rework process characterization, all those kind of things. And then finally, you have to make sure you send it to the sorting, do the test, end of line data, and then do the white paper implementation and spec high volume. It's not that easy. Now, doing all those things, next is the chronology of technical notes. Just to ask you one thing, Dr. Bini L'Oreal, how much time do we have?
About 20 minutes, up to 20 minutes, please. Go ahead. Yeah, please.
All right, so chronology of technology nodes, as you can see here, it started from the 10 microns in 1971. Obviously, this nanofabrication I have been talking about is based on the CMOS, complementary metal oxide semiconductor. So CMOS technology was developed in 1959, 60 kind of, and then Intel started in 1967, but then they, just in the beginning, the first thing they started in 1971, 10 micron, but then gradually the chronological order, 74, 6 microns to 3 microns, and then 1.5 microns, 1 microns, and then slowly getting shorter and shorter. The size is smaller and smaller, 800 nanometers, 600, 350, 250, 180, 130, 90, 65, 45 nanometer get width, and then 32 nanometers. That is when I started in 2009, when they were just starting 32 nanometers. So that is the time when I was hired. And then we did 22 nanometers, 14 nanometers, and 10 nanometers. So I was working in 10 nanometers, but then in 2017, as I said, I moved to start for Samsung. And then 7 nanometer, and then the future, who knows, 5 nanometer and 3 nanometer to 2022. But then it all depends on how things go, because you can't just predict what is going to happen. The thing is, you can't just put, for example, you can't just put 2 atoms together and then, okay, I'm done. So there has to be some strategy. As the size gets smaller and smaller, it gets more challenging. So then, as you can see here, the exposure type, you can see here is 130 nanometer. The KRF is krypton. For this is the laser type 248 nanometer, 90 nanometer, and 65 nanometer. 45 nanometer is ARF. So that is immersion, I means immersion, and then 32 nanometers. And then when you go to much smaller, then just the ARFI doesn't work. And then you have to do the double patterning, and then you go further down, and then you have to do the self-aligned double patterning, triple patterning, and then you go further down, you have to do the self-aligned triple patterning and self-aligned quadruple patterning, and then 5 nanometer you have to do self-aligned quadruple patterning, and then there is a next generation lithography NGL that is called the DSA that we'll have on the next slide. So one thing I wanted to mention here is the high K metal, that is the hafnium that we used in 45 nanometer, just to overcome the quantum mechanical tunneling leakage. And this was implemented in 45 nanometers. So this is kind of the technology nodes. You get much smaller and smaller to get the device much faster and efficient from the power perspectives and the leakage, everything else. So, all right. So DSA is something, the next generation lithography. This is still, people are working on it, but this is not very well defined yet, but this is just a concept. You use a different type of block of polymer, because no any facility is using so far, and that's the reason I can just give a little bit of this. This is block copolymer, A block and B block, and then they get self-aligned, and that's the reason this is called directed self-assembly. So this leads any patterning that you make follows whatever is already there. So it follows that. And from the time constant perspective, I don't want to go into detail about this. So now, so far I have been talking about the research corporate facilities and what they do and what the fab culture is and what you would be expecting yourself to do when you get there. But then research at Texas State University, well, I am in Texas State University this last year, because that is also something I had to mention, because I wanted to go back to academia, and that's the reason I joined the Texas State University last year, and now I'm good. So then we have the nano fabrication fab also, not like Samsung Intel, but then we do have the lab. It's not lab, it's kind of a fab, not the manufacturing type of fab, but the research type of fab. We do have that. So we do the semiconductor device integration type of thing. We have the molecular beam epitaxy. We do the growth and characterization, device integration also, semiconductor and biological systems. We have the atomic force microscopy lab. We do the semiconductor, optical fiber, and biological systems. So characterization of medical and materials application. We use several type of like DNA, and then mix with other component, and then do the characterization, atomic force microscopy. There is 3-5. I'm not involved with that, but I just wanted to mention here what research facility we have at Texas State University. 3-5 is gallium arsenide type of thing. People are involved in that. Computation and experimental, both. Little bit of experimental, mostly computational work. Personally, I had started the computational work in the beginning of my PhD. I did some, but then later on, when I decided not go back to Nepal because of my children, I had to get settled down here in United States. So then I changed my discipline. Discipline means the research discipline, and then I became experimentalist in nanoscale science engineering and medical physics. So nanofabrication, MBE, AFM. So one of the research, most recent projects that I've been working, there was a good funding opportunity from Department of Defense. They had the funding opportunity on this project because they wanted to get the device integrated, the laser device integrated, so they could use it in kind of separate thing, the optical fiber sensors for their purpose. Okay, so then started working on it, but then they had this strict requirement that you can't just claim, okay, the device you made, and then it takes 5 years. Their timeline was 18 months, but then you have to, in the proposal, you have to write that, okay, you are collaborating with a foundry. Foundry means the corporate facilities who do the foundry business. So then foundry, because any fab in academia, they don't have that type of facility. So they are the only ones who can do this. So, but then most fabs integrate on silicon. Okay, their facilities, they work on the silicon. They integrate any device on silicon, starting from silicon. But then this was to be done on the germanium. So because the silicon, there are certain limitations that this doesn't work. This photonics, this optoelectronics mechanism doesn't work there. So then the challenge is to integrate on germanium, and that was the big challenge. So the fab equipment cannot do it, and then we have started on our own in our own fab lab, but then we'll see where it goes. But then the question is, why germanium silicon tensile strand? Why? This is our project. So we want to get the working laser integrated germanium, tin, and carbon, this LY composition. But then why germanium, silicon, and carbon tensile strand? The reason is the current silicon fab tools that I have been talking about so far require for silicon compatible laser, because they integrate on silicon. So it has to be electrically pumped. It's not optically pumped mechanism that can be done there. So it has to be electrically pumped. And also it has to be fabricated on silicon within the CMOS process flow, complementary metal oxide semiconductor process flow, the process flow that I talked about briefly. And then it has to emit around 1550 nanometer. So you can use the chip and can connect to the fiber optic network for their use in the sensors. Okay, so those are the requirements. But then no any device so far has met all these three requirements, and that is the reason people started doing the modeling. So this is this modeling is from the computational work. This is not our work. But then we analyze the data and then said, saw the modeling of tensile strength 0.25% tensile strength. N-type germanium will be the thing that you can make it experimentally and get the device integrated. And that is very exciting modeling result. But then us being experimentalist, working in the fab lab with the equipment, okay, is it possible to make it? And that is the reason we started working on it. So then the question is, why only 25% strength? It could be, so the data so far shows that if you have 2% tensile strength germanium, then the germanium has two band gaps, direct band gap and indirect band gap. So then at 2% tensile strength, it becomes the direct band gap. And then you are done. But then the problem is, another challenge is, when it becomes the direct band gap, then the light you get is 2500 nanometer. It's not 1550 nanometer. So the another requirement is you have to have 1550 nanometer, so you could connect it to the fiber optic network. So then that doesn't meet there. And that's the reason you have to make sure you get what you want. So then 0.25% of tensile strength, the modeling data shows that would do. But then there are so many challenges there. So this is something I wanted to show. This is already something I talked about, the germanium direct band gap and indirect band gap. And then you want to make it tensile strength, so there is a slight decrease in the gap between the direct and indirect. And then you have to do the calculation, how much injected electrons, how much injected holes you can do, so it gives you the light that you want to make the device integrated to get the laser. But then why tin then? Because so then you have the better control on the engineering, band gap engineering, by controlling the silicon content. Also you have the smooth topography, improved topography in the interface between the two layers, and defectless to the most part. And then reduced process temperature also, because of the low, if take that is called the mixture proportion temperature of germanium silicon alloys. And then these are the reasons you choose germanium silicon. But then why carbon then? We dope with carbon, so molecular beam epitaxy finds a proper strain balance in the matrix with the tin flux that you shoot it with in the molecular beam epitaxy. And then another thing is also, this provides the improved incorporation of silicon when you dope with carbon in that matrix. And this is because of the compensation of the compressive strain caused by tin and the tensile strain induced by the silicon to obtain the minimum energy in germanium matrix. So all these things need to be taken into account, and all these things, that is what we have done some work, and this is exactly from our lab. So you can see we have deposited and we have started the growth, and then we have done some characterization also. The 2D image, FM, atomic force microscopy images. With the naked eyes, you will see completely like nothing. But then when you do the AFM images, you see like this. And then 2D, 3D in the middle, and then the top view on the right. And then you can see the TEM, transmission electron microscopy image also, that can show you, that can tell you the silicon and then germanium tin on top of the silicon layers. So that is the cross-section view. It's not the top view also. When you do the TEM, that is another technical things that you have to be expert on. So then you have to cut certain direction so you can get the cross-section view of the image like that. And then you do the characterization to make sure you have the right proportion of the tin and germanium and the carbon. So you do the Raman spectroscopy, you do the component detection by use of the EDX, energy dispersive X-ray also. X-ray is also my thing that I did when I was doing my PhD for the medical physics, dosimetry, cancer research, diagnosis, all those kind of things. So X-ray. But the challenge is the growth quality, as I say, topography, proportion, strain, percent, gain, the stimulated gain, optical gain, I mean. Injected electrons or holes is also another challenge. You have the formula. You might have seen I have not used any mathematics on the slide because being experimental and being someone who works directly, bringing things into real life application, you don't use that much. But then there are certain mathematics things that we use that I didn't put here, maybe next talk. And injected electrons, something that is another, how much you inject so you get the right amount of the laser. And the circuitry design you have to make. The work is still in progress with hope to get working device integrated. And that's all for tonight, today, at least in Nepal. I wanted to do something in the breakout room because we didn't have any break. So I wanted to put here food for thought in breakout rooms, but then I don't know if we have time, but then I just wanted to put it here, at least food for thought for all of you, if someone is planning to come to United States. If you were or are given an opportunity to choose between a corporate and a university for your future career, what will or would you like to do and why? It's individual choice. I just wanted to put it here, so something. Um, we don't have, I think Dr. Orial said we have 20 minutes, so we don't have that much time to separate the breakout rooms and put maybe 10, 20 people in one room. And then normally when we do the online teaching here, we generate breakout rooms and ask the students to do some brainstorming. So just like this is nothing, but just like you guys also do there, right? So, all right, so that's all. And then I wanted to hear if we had the breakout room separated for the brainstorming, what would you do? Things to include the corporate only, if you want to go to the managerial path or technical path or hybrid of the two, or academia only, teaching, research, or both, service, hybrid, combination of both, corporate, then academia, and academia, then corporate. I'm in the middle basically, from academia to corporate, back to academia again. So it's individual choice. That's all from me and this time. And thank you again, Dr. Benilial, for inviting me. It was a pleasure after such a long time. It was a pleasure meeting with all of you and seeing really nice combination of everything I could expect from you guys. PhDs, faculties, masters. Thank you. Or if any questions, we can talk about it.
Thank you. Thank you very much for this in-depth and wonderful talk in all respects. For students, for PhD students, for faculties, this talk is of course wonderful. Thank you. Now I hand over Raju sir. Please, I request Raju sir to take care questions if you have, if you have seen in the chat box, or please, Raju sir.
Okay, thank you, Benil sir. And first of all, thank you, Dr. Mahato, for this wonderful insight in basically in fabrication, which we usually do not discuss. We usually only hear about the results. Okay, I request all the participants to raise hands. Some of you have already, if you have a query, so that I can go to the order. So I request first, Dipendra Parajuli, please go ahead. Unmute yourself and go ahead. Please ask.
Okay, are you hearing?
Yes, yes.
Thank you, sir. First of all, thank you, Benil sir, Raju sir, for organizing this interesting talk. And then thank you, Narayan sir, for overwhelming presentation. It's very good. In fact, first, I think regarding your question, the way you are taking that is very good. First, you went to corporate
Mhm.
and then to research,
Mhm.
so that now you know what are the important things in research and what we should do in research. So that is the very best way. I think if anyone want to means join in this research activities, that is very good way. The way you are taking is very good. And the next question I have: what is the role of oxidation in this process in between? And the next thing, if we are going to buy an electron microscope in our laboratory, then which would you prefer? TEM, AFM, SEM first, so that we can get so many advantages in our laboratory. That's my question.
So, where are you right now, in Nepal or in United States? What is
No, I am here in India.
Oh, you are there in India. So, okay. So oxidation is kind of creating passivation type of mechanism. So you can create other features and without any short circuiting the device. So that is the whole purpose. The details, because oxidation you use different steps in the process. It's not only one step, you use at different steps. But in the beginning, when you have the bare silicon, you first do the oxidation, and then after that you start creating the channels and create the source and drain. So you will start making that oxidation there, so you can expose by the implant. You only leave one area open from the oxidation, where you want to shoot the use the implantation to do the source and drain. The other area of the wafer is not exposed. So for that purpose, you put the oxidation there. All right. So regarding your question about the TM, SEM, and AFM, it depends on what you want to pursue. For example, if you have to do the characterization of anything in your project, one thing is not enough. So it's the combination of everything. For example, you use the AFM, and then for the AFM, you get the topography of the growth that you have had in your project. But then if you want to do the composition analysis, then you have to do the Raman spectrometer, Raman spectroscopy also. So you combine the AFM with Raman spectroscopy. Then sometimes the scanning electron microscopy, that image is also sometimes very clear, but then there are certain samples, certain materials that you want to use the AFM. But in the AFM also there are different techniques to use the AFM, and depending upon your sample, you may have to use different techniques in the AFM. Now, TEM, transmission electron microscopy, if you have to, like for example, you have the sample, you deposit it, one layer on top of the other, you did the characterizations, and sometimes you see, okay, there is something issue going on. Then from the top view, you cannot see. From the scanning electron microscope, you can take the picture from the top side. But then in the cross section, if there is one layer defective as compared to the other, then you want to cut it, the sample that you have made, the growth you have made, and then you put in the TM, and then you take the picture of the cross section. So different equipments, they have the different features, different type of use. So it depends on what you want to pursue, depending upon that. I think if you have good funding, you should have all. If you want to be rich in your lab, you should have all.
Yeah,
That's good.
true.
Okay, thank you. Next, I request Gopi Chandra Kafli sir. Please go ahead.
मलाई हो
हजुर हो गोपी जी
ए ल ओके ल दिपनारायण सर ल एकदम थ्याङ्क यू भेरी मच फर योर भेरी नाइस प्रेजेन्टेसन्स एन्ड भेरी फ्रुटफुल इन्फर्मेसन्स टु अस र आई हेभ द रिगार्डिङ दिस आई हेभ द वान क्वेसन्स टु यु रिगार्डिङ GESNC GESNC वेदर इट इज यो चाहिँ के डिभाइस हो युस्लर एलोइज टाइप हो अथवा के हो वान थिङ इज द्याट अनदर वान इज इफ इट इज द युस्लर एलोइज you give the strain on it, and if you give the strain on it from means strain you increases from 0.2% to 25%, and within that range still it is in the semiconductor it is यो semiconductor रहिरहन्छ कि or in which percentage lost its behavior?
So 2%, if you get to 2%, then it becomes direct gap, direct
Pardon?
band.
Okay.
If you increase the strain to 2%, then it becomes direct band gap. There is no indirect band gap. But then that will give you, that can give you the laser, but then the laser wavelength will be 2500 nanometer, close to. But then you want 1550 nanometer, so you can connect it to the optical fiber to make the sensor working for your purpose. So you want the requirement is 1550, and that is something you cannot get if you make it 2% strand, tensile strength. So you can go to 25%, 0.25% to, as you said, 0.45%, but then there is other things affecting there. The more they strain, how much the transition, how much injected electron or holes you have to inject to make sure the transition is happening the way you expect it to be. So those are the things. Otherwise, the question you asked, what is the extent to which you can lose the band gap, indirect band gap mechanism? And the answer to that question is 2%.
Okay. यो Euler alloy type हो?
हजुर?
यो Euler alloy नै हो कि अर्को type हो यो?
यो अर्को type हो.
Okay.
Okay, thank you.
यो त्यति युजमा अहिले आइसकेका छैन. त्यसैले यो डिपार्टमेन्ट अफ डिफेन्सको यो प्रोजेक्ट भर्खर आएको थियो. यो चाहिँ वर्किङ, यो कन्टेक्स्टको वर्किङ लेजर अहिले बनिएको छैन. यो भेरी न्यू.
Okay.
Next, I request Sanju Shrestha madam to go ahead, please.
Okay, Mahato sir, thank you. Thank you for your very much informative presentation. सुनिराख्नु भएको छ है?
सुनिएको छु.
मेरो question चाहिँ नि, before going for fabrication, are you using any specific software for modeling such devices?
Yes.
Like TCAD, etc., or else?
There are other types of softwares. They keep among themselves. But then, yes, for the modeling, there are so many data analysis tools that research corporate facilities use. They have their own type, like Crystal Ball, Discover, some Pathfinder also. They develop their own. Many softwares, they develop their own. They have their software. I am not the software person, but then
okay, no, just I want to know the name of the software. Which one you are using?
So I used to use Crystal Ball.
Crystal Ball. Okay, that is specifically for CMOS, etc., or else?
I worked in CMOS. Yes.
So Crystal Ball is suitable for CMOS. That I understand, or what?
Yeah. That is what I have been using. Yes.
Okay. Thank you.
Where are you? I have another question. I know you were in the second year when I was in the first year, so I think I have seen you in the department. So where are you?
I am batchmate of Rajeshwar. And
yeah, I know.
Yeah.
She's at
I'm in Center Department now.
At CDP.
Yeah.
We are in the same place where you left us.
So, yeah.
Okay. No, not in KU. Not in KU. Not in KU. Okay.
Okay, just
so
just a minute.
Please go ahead.
Do you have any idea about TCAD software?
No, I have not used that.
Okay. Okay, thank you.
There are no more raised hands, but there are questions in the chat. So I will ask it myself. This is what maybe they have microphone issue. Okay, it is from students. So I ask in Nepali. Are you taking any PhD student from Nepal?
So we have one PhD student right now from Nepal, and we have one master's from Nepal. We have some undergrads, but one master and one PhD from Nepal. So yes, of course, if someone is interested, they can send the application. There is a procedure, and then the university procedure. So they have to go through but I can write a recommendation. I can recommend once we receive the application. Yes.
Okay, thank you. So it is clear that the students should go to to contact him or go to Texas State University website and see the process.
Yes.
And he will be happy to recommend. And one more query, also in the chat box and also myself. Many people here like Sanju Madam, Gopiji, they are doing similar things, computational and also some experiments. And our problem basically here, I'm not doing it, but I know the problem is characterization. So in the future, would it be somehow possible to collaborate so that you can help them in characterizing if they send samples? I don't know how that is possible, how the aging effect will take place. Just a query.
Yeah, that will be another challenge, the aging, for sure, because in the fabrication process, aging is very important because you can't be late even by 15 minutes, something like that. But then getting the sample from Nepal here, that will be another challenge, but it depends what kind of sample you have prepared and how we can handle that. But if that is something we can do, then of course, yes, for the characterization, anything, to whatever extent I have to help, yes, I'll be more than happy to help.
Okay, thank you so much. And Binil sir, because there are no raised hands and I don't see any issues in the chat box, I thank Deep Narayan ji once again and all the participants, and I switch back to Binil sir, please.
Thank you. Thank you, Raju sir. Finally, I would like to thank you again, and hoping probably after a month or after a couple of months, as per your plan, schedule, and we wish to organize another, as you said during the talk, another seminar. So just by saying on the behalf of Central Department of Physics, to do plan for another seminar. Thank you, Deep Narayan sir, for this. So I would like to say good night. If you have to say anything finally, so please say, if you have to say something to the student, then I will close the session.
Yeah, the only thing I can say is, yeah, it was a pleasure. I personally thank you for inviting me, and it's been so exciting that I got to see all of you after such a long time. And then all the participants today, mostly the PhD students. Yeah, it's been a pleasure to be among all of you. And yes, of course, after a month or so, maybe next time, whenever there is opportunity, I can present another talk. That's all. So I think we are good. Thank you so much again. And yeah, have a good day there. I'll have a good night here. And then, so you mentioned maybe to Dr. Sanju Shrestha. So you are involved in the research, similar fabrication type of research there? You are muted.
You are muted, Sanjuji. Okay, wait, I will unmute you.
Sanju, please.
You are still muted. Now, oh, you are still muted.
Okay, now.
Yeah, are you getting my voice?
Yes.
No, now
okay,
I'm getting.
Okay, actually some of my collaborators are doing work in resistive RAM memory devices, and I have to do some theoretical work on that. That job is just going to be started.
Okay, cool.
Resistive RAM memory devices.
Okay, all right, that's good to know.
So probably I have to start using TCAT, TCAD or TCAD? TCAD, I suppose.
TCAD, yes.
I have to learn TCAD, etc., and do my work. That's why I'm asking to you.
No, I got it. I got it. Yes, I have not used that software, but if I see it, then I'll have to just know how it works, and then I'll get it working. Yeah.
Probably I have to work on neuromorphic devices.
Yeah. All right, that's good. Good luck. Let me know if I can help in the future.
I have not even started. Means I'm just going through learning about this. So later on, I'll contact you if it is needed.
Yeah, sounds good.
Okay, thank you.
Yeah, you're welcome. All right, so I think that's all from my side, and I think we are good. Anything else from any of you? If not, then I think we are good.
Okay, thank you, Deepnanji.
Yeah, my pleasure. Yeah.
Is no any further answer?
One question, Vinil sir, your question.
Yeah, please.
किनभने सबै फिगर जति नयाँ भन्नाले मेरो टाइमदेखि अहिलेसम्म नयाँ मात्र देखेको छु। पुराना मध्ये कोही देखिएन, जस्तै डाक्टर उदयराज खनाल सर, उनीहरू सब रिटायर्ड भइसक्यो है।
हजुर, उहाँहरू सबैजना रिटायर भइसक्नुभयो। इभन जीवनज्योति नकर्मी सर हाम्रो उहाँ रिटायर पनि भइसक्नुभयो। अलिकति एज पनि केही सरहरूको चाहिँ त्यति एक्टिभ हुनुहुन्न, केही सर एक्टिभ हुनुहुन्छ। उदयराज खनाल सर चाहिँ रिलेटिभली वर्क नगरे पनि पब्लिकली चाहिँ लेक्चरहरू गर्नुहुन्छ, क्लासहरू लिनुहुन्छ। अल सिनियर्स दे आर रिटायर्ड। झा सर इज एक्टिभ स्टिल। झा सर चाहिँ एक्टिभै हुनुहुन्छ अहिले।
रिटायर्ड हुनु भयो?
हजुर,
उहाँ अहिले डिपार्टमेन्टमै हुनुहुन्छ कि?
हुनुहुन्न, उहाँ रिटायर भएको धेरै भइसक्यो। तर आउनुहुन्छ, कहिलेकाहीँ डिपार्टमेन्ट आउनुहुन्छ, झा सर आउनुहुन्छ, गुरुङ सर आउनुहुन्छ। गुरुङ सर पनि हामी इन्भाइट गर्छौँ, हामी बोलाउँछौँ, लिएर आउँछौँ है। लगायत सबै सरहरू, ब्याउ सरहरू सबै रिटायर भइसक्नुभयो। सबभन्दा सिनियर, सबभन्दा अब रिटायर हुने हाम्रो पालो भएको छ।
मिश्रा सर नि? मिश्रा सर, पौडेल सर?
मिश्रा सर, पौडेल सर चाहिँ यतै हुनुहुन्छ। मिश्रा सर त्यतै हुनुहुन्छ, युएसमै हुनुहुन्छ कति समयदेखि। छोरा कहाँ हुनुहुन्छ। त्यस्तै केले सर पनि अहिले हुनुहुन्छ, केदारलाल श्रेष्ठ सर। उहाँ अलिकति अलि बिरामी हुनुहुन्छ, तर उहाँ पनि अलिअलि एक्टिभ चाहिँ हुनुहुन्थ्यो। र अहिले हाम्रा सिनियर सरहरू लगभग हामीले बोलाए हाम्रो कुनै प्रोग्राममा एकदमै खुसी भएर आउनुहुन्छ। दे आर भेरी ह्याप्पी। र उहाँहरूले हामीलाई स्वागत पनि गर्नुहुन्छ।
खुसी लाग्यो।
अब कम्प्लिटली जेनेरेसन चेन्ज भएको छ जस्तो। सेन्ट्रल डिपार्टमेन्टमा, कलेजेसहरूमा, थ्रु आउट फिजिक्स डिपार्टमेन्ट अफ तिरुवनन्तपुरम युनिभर्सिटी, जहाँ पनि जुन पनि कलेजमा गएर हेऱ्यो भने त्यहाँ यङ्गरहरू नै हुनुहुन्छ। अब हामीले राम्रो गर्न सक्यो भने, हाम्रो जेनेरेसनले राम्रो गर्न सक्यो भने अभियसली राम्रो हुन्छ। त्यसैले जिम्मेवारी छ र हाम्रा स्टुडेन्टहरूले अझै बेटर गर्नु पर्यो। यसमा हामी केही छलफल गरौँला। मैले केही कुराहरू सोचेको छु, 2-3 जनासँग, 2-4 जनासँग बसेर, लाइक माइन्डेडहरूसँग बसेर हाम्रो डिपार्टमेन्टको लागि कन्ट्रिब्युसन हुने किसिमले हामी छुट्टै एकचोटि बस्नुपर्छ। दिप्राणजी, थ्याङ्क यू। इन्ट्रेस्टको लागि धेरै धेरै धन्यवाद है। ओके, गुड नाइट। Raj sir, probably he already left.